Hi students, welcome to VEDA Gate Academy. Now we can able to discuss the analog circuits, right? So that is the applications of electronic devices. So what are the contents of this analog circuits? First you can able to examine. So now you are able to discussing that analog circuit, students. So that is the applications of your electronic devices like diodes, BJT, FET, MOSFET, you know those things. So whose applications that you may going to learn in this analog circuits. So in this analog circuits, first you start with what means diode circuits. So the first chapter of this one now, the diode circuit you can call. So under this diode circuits, now I can able to discuss the applications of diodes. What is that one means? So diode is a switching device, you know. So that can be applicable to use in rectifier circuits. A rectifier is one that convert AC into DC, you know. So under these conditions, now I can able to discuss the applications of the diode circuits. First of that one is what means? Rectifiers and power supplies. So it is the application of a PN diode, you students. So rectifier is one that convert AC into DC, but the output of the rectifier is not 100% DC now. So that it is having both DC and AC components. The what are the AC at the output of a rectifier can be filtered out by using a filter circuit, and after that it can be regulated with the help of a regulator. Who to be used as a regulator, you know, Zener diode to be used as a regulator. All these concepts you may learn in this chapter, right? Rectifiers and power supplies. Other than this, under diode circuits, you know, one more thing you may discuss here, clipping and clamping circuits. Clipping and clamping circuits. What is the clipping circuit, sir? Clipping circuit is used to clip, that is nothing but remove a selected portion of the signal waveform, that is either positive cycle or negative cycle, part of positive cycle or a part of negative cycle. So the selected portion of the input signal waveform can be clipped off by using a clipping circuit. That is the application of a diode. Right along diode with some chargeable capacitor, you may able to get a clamping circuit. So using clamping circuit, you can shift the signal level towards either positive side or negative side, you can call. So that to be done by the diode with help of what means some chargeable capacitor. So such type of things you may discuss under this clipping and clamping circuits. Okay. So under diode circuits, these are the two things we may going to discuss. Next, now come to the BJT part, students. Second one is BJT related now, bipolar junction transistor. So under this BJT related now, we can able to examine what, students. Okay. So BJT concepts first you can discuss. Next, under this BJT concept, now you can able to examine the biasing techniques. So thermal stabilization and biasing technique, students, it is most wanted for BJT, because BJT in which the output is not stable due to minority carrier effect, that is mostly dependent on temperature conditions. Okay, so the output is not quite stable. If such type of BJT, if I use in amplifier circuits, the output is distorted. So before using the BJT body for amplification, so first of all you need to keep that output is stabilized. How to keep that output to be stabilized, sir? That to be done by what means biasing techniques. So all these are the DC biasing techniques, students. So different type of biasing techniques, fixed bias, collector bias, emitter bias, cell bias, like this. Different type of biasing techniques are there. All that one you can able to learn, right? Next one, students. Small signal model of BJT. Next one, students, we may going to discuss a small signal model of a BJT. Right, what is the AC equivalent model of a BJT? Small signal low frequency model as well as high frequency model. Different type of models are there. RE model, T model, hybrid model, RPi model, like this. Different type of small signal equivalent model of a BJT that you can able to examine, students, under BJT. So biasing techniques. and small signal model of BJT you can discuss. Next, the application of a BJT, I think that you know students, that to be what sir means amplifiers. So now I can able to discuss students BJT amplifiers, right? Not only that amplifiers using BJT, we can also discuss that amplifier circuit using MOSFET also. So amplifier circuit using BJT first I discuss students. So frequency response of amplifier, multi-stage amplifiers, all these type of things that you may going to discuss in this amplifiers part. Okay. Next one of that one students, feedback amplifiers. So next you can able to discuss what that means. So feedback amplifier students, right? What is the purpose of feedback in this amplifier circuits? All that concepts, positive feedback, negative feedback. So what is the effect of this feedback in amplifier circuits? All that one you can able to examine in this amplifiers part. Okay. Next, we can able to examine the integrated chip device of an amplifying circuit, right? What is that one, sir? Means op amp. So you know that students, the first amplifier device in our electronic circuits is nothing but vacuum tubes. So the first era of electronics starts with vacuum tubes, but vacuum tubes are large in size and as well as expensive, consume more power. That should be replaced by the semiconductor body of BJT MOSFET like this. And again, with rapid development in the semiconductor technology, now we may consider that integrated chip element of amplifier circuit, that should be, you know, operational amplifier circuit. It is one of the most fundamental element in our analog computers to do that analog computations like addition, subtraction, all these things. Okay, so that concepts you may discuss students. Operational amplifiers. Confirm. So under this operational amplifiers, what are the concepts of operational amplifier you may learn, right? What is the application of op amp in analog computers, that is adder, subtractor, integrator, differentiator, log amplifier, anti-log amplifier, all that type of things you can discuss. Other than this, in this operational amplifier also you can discuss, right, operational amplifier based oscillator students, right, those sinusoidal oscillator and non-sinusoidal oscillators of astable, monostable and bistable you can discuss. Other than this, op amp based what that means, schematic trigger, comparator circuit, all these type of things we may going to discuss students. Other than this, in this operational amplifier chapter, we can also examine some IC circuits of what that means 355 timer. I think that you know students, 355 timer to be used as a what that means a stable and a monostable multivibrator. So what is that IC 355 structure and how it to be used as a stable and monostable, all these things to be discussed in this chapter students. So operational amplifier plays a very important role for both EC and EEE streams, and it can carry good marks in this one students. So it can able to carry around 2 to 3 marks, right? So this is the operational amplifiers you can call. Other than this, next one of that one students, next one is what that means, MOSFET amplifier students. Next one is MOSFET. So under this MOSFET, what you can do, discuss students. So MOSFET concepts you can learn. Concepts of MOSFET. MOSFET biasing techniques. Okay. And MOSFET as an amplifier. So these to be you discuss in this MOSFET concepts. So under MOSFET, you can discuss the concept of MOSFET. And next you can discuss the biasing techniques. But biasing techniques of MOSFET is too simple as compared to BJT. Why, sir? Means MOSFET is quite stable than compared to BJT students. And as well as how to design that amplifier circuit using MOSFET. All this one you may going to learn. So these are the concepts that you can able to discuss in this analog circuits for GATE exam. Confirm my option students. So what are the thing you may discuss means, first you start with the diode circuits. Under diode circuits, the applications you may discuss, rectifiers and power supplies. Next clipping and clamping circuits. Next, come to the BZT concepts. Under that BZT concepts, now I can able to go for its applications as an amplifier. Before that amplifier, we can able to discuss the most required things before amplification is biasing techniques, and as well as what is the small signal modeling of BZT you can call. And other than that, so to keep that output to be stable in amplifier, one of the concept you may introduce that is called as a feedback concept. What are the feedback concepts? All this one you can able to learn in the feedback amplifiers. Right, an integrated chip based amplifier circuit called operational amplifier we can discuss. So in this operational amplifier itself, we can also discuss oscillators concept also. Okay, so next one is what means what I told you, MOSFET concepts. So along that MOSFET concepts, you can discuss biasing techniques of the MOSFET as well as MOSFET amplifier circuit students. So what are the reference books so that you can able to go for this one means? See this one now? So one of that one is what means Microelectronics by Sedra and Smith students. Microelectronics by Microelectronics by Sedra and Smith. So one more is what means electronic circuit analysis and design by Donald Newman students. So Donald A. Newman. Okay. So electronic circuit analysis and design. So these are the most suggestible books for this analog circuit part, right? So these books are also helpful for EDC condition also. EDC part also, the same books you may going to refer. And let us see this one now, students. So what are the weightage of these analog circuits in the GATE exam for EC as well as for EEE students means? For EEE students, these corresponding analog circuits carry around 5 to 7 marks, students. So around 5 to an average, it should be carry 5 to 7 marks. Suppose if you go for ECE students, it should be carry around 8 to 10 marks. For EC persons, it will be carry around 8 to 10 marks, students. For EEE students, it can carry around 5 to 7 marks. So first now you can able to start what means diode circuits. Before going to diode circuits, now I can able to give a brief idea about semiconductors, because so according to the syllabus, so directly can able to start diode circuit. But first of all, now I can able to give a brief discussion about semiconductors, because in the case of your applications, you may use the words drift to diffuse and all these concepts. So first of all, you must also have an idea about that drift to diffuse and all this one now. So for that, now I can able to start some introduction about semiconductors. After that, now I can able to go for diodes introduction, and then you can able to come back to your original concept that is called diode circuit application, students. Okay. So first one I can able to go for the introduction to semiconductor, students. So first I start to you introduction to semiconductors. Okay. What's another, students? Introduction to semiconductors. Now I am going to be start. So you know that based on the electrical conductivity, the solids are classified into what means conductors, insulators, and semiconductors. Conductors, insulators, and semiconductors. Confirm, students? And these materials are easy to distinguish. These materials are very easy to distinguish based on what means energy band diagram. Confirm my option, students? So based on the electrical conductivity, so the solids are classified into conductors, insulators, and semiconductors. And once again, you can able to distinguish all these three particles with help of energy band diagram. So what is the energy band diagram means? You know that according to the Bohr atomic model, in a given atom, what are the electrons? You say all the electrons not have the same energy. So in a given atom, what are the electrons are there? All those electrons never have the same energy. They have random values of energy. So how do you know the energy probability of an electron in a given atom, sir? That to be known by means of a energy band diagram. So it's 100% similar to what means progress report of a student. I think that a student may learn number of subjects in his course, but he may not score same marks in all papers, all subjects. But how do you know the performance of a student means by means of preparation of progress report. So by the help of progress report, you know that what are the marks scored in each paper and what is the total marks. By that you calculate the average and thereby can able to estimate the performance of a student, whether it is average students or above average or nothing but what you can call good or excellent. This type of thing you may discuss by means of a progress report. In the same manner, in a given atom, all the electrons not have the same energy. They have random values of energy, students, so that we can able to discuss the probability of energy of an electron in a given atom by means of its energy band diagram. Why I say this energy band diagram, students? Using energy band diagram, one can distinguish conductor, insulator and semiconductor very easily. So the distinction between conductor, insulator and semiconductor to be done very easily with help of what? Energy band diagram. What is that energy band diagram? I show to you. Check up this, students. So what I told you, based on electrical conductivity, okay, we have conductor, insulator and semiconductors. Okay, conductors, insulators and what's that means? Semiconductors you can call. Conductors, insulators and what's that? Semiconductors. So this can be distinguished usually with help of what's that means? Band diagram. Okay, which can be distinguished easily with the help of what's a energy band diagram, students. With help of what? Energy band diagram. First I discuss that energy band diagram, then I can able to discuss conductor, insulator and semiconductor, and come back to your required semiconductor, and in that semiconductor again you discuss intrinsic and extrinsic and what are the conditions of that. Then you can discuss next current mechanisms, all these fundamentals. Okay, so first I check out what sir means energy band diagram, students. Energy band diagram you can call. So what I told you, according to the condition of Bohr atomic model, all the electrons in a given atom not have the same energy. They have random values of energy. So what is the probability of energy in a given atom known by energy band diagram? So this energy band diagram contains three partitions, students. One is Valency band, other one is conduction band. These together separated by a gap called as a forbidden energy gap you can call. Right? Forbidden energy gap. Understand, students? Okay. This can be distinguished by means of what means forbidden energy gap. So what I told you, the probability of energy of electron in an atom is known by energy band diagram. So in a given atom, what is the probability of energy of an electron is known by what, sir? Energy band diagram. So what I told you, students, it has three partitions. It has three partitions. What are those ones, sir? Valency band, conduction band. CV means conduction band. VB means valency band. These together separated by means of a gap that is called as a forbidden energy gap, simply called energy gap, students. Forbidden energy gap are simply called easy. Okay. So now I can able to indicate that energy band diagram, students. See this one now. So this is the energy band diagram structure, students. So this will be called Valency band, students. This will be called conduction band you can call. Okay. These together separated by a gap that is called as a energy gap. So this is the energy band diagram structure, students. So Valency band, conduction band together separated by gap is called as a energy gap you can call. Confirm my option. So yes, for now, according to the condition The energy range of electron is from minus infinite to plus infinite, students. The energy range of carrier is from minus infinite to plus infinite, means upper level of conduction band, lower level of valence band are undefined states. And you are intimating the lowest energy of carrier in conduction band as a EC. Just it is a notation. So EC stands for the lowest energy of the carrier in conduction band. And what is this one here? EV stands for highest energy of the carrier in valency band. Highest energy of the carrier in valency band. And this energy difference is called as a forbidden energy gap, students. That can be called EC minus EV. That can be called what, sir? EC minus EV, right? Sir, what is the valency band? Sir, valency band is the range of energies. Valency band is the range of energies considered by valence electrons. Right? Understand, students? It is the range of energies considered by what? Valence electrons. What is the meaning of valence electrons, sir? Valence electrons are those, right, which are binded with the nucleus or which are binded with the concerned parent atom. And such electrons are not free. Confirm my option, students. So valence electrons are those are under the influence of nucleus, right? And such electrons are not free because they are binded with the nucleus. Sir, according to the Bohr atomic model, when an electron becomes as a free, means the electron can become look like be free whenever it is completely out of the nucleus effect. Whenever it is completely out of that binding restrictions of the nucleus. Under such condition, the electron become free. And such electron can travel anywhere in the given crystal to get the conductivity. So simply in our language, students, it is the range of energy considered by valence electrons which are not free. So simply you say that it is the area related to binded electrons. It is the energy range related to binded electrons. So as long as the electron in the valency band which is not free. Confirm? That's called as a valency band. So first of that one I told you, students. Valence band now I am saying. So what is this valence band, sir? It is the range of energy considered by what? Valence electrons, I told students. It is the range of energies considered by valence electrons and which are not free, students. Which are not free. So simply you remember it is the area related to binded electrons. So as long as the electron in the valence band, that's not a free. Sir, what is the other one? Conduction band. Conduction band is the range of energies considered by conduction electrons. Sir, who to be called as a conduction electrons? Sir, means conduction electrons are those which are 100% free from the effect of the nucleus. What are the electrons which are 100% free from the effect of the nucleus? Those are called as a conduction electrons, right? And range of energies considered by such conduction electrons is called as a conduction band. So in our language, it is the zonal area related to valence electrons of not free. So it is the zonal area related to conduction electrons which are free. So it is the area belongs to binded electrons. It is the area belongs to free electrons, we can call. Confirm? So next of that one, what I told you, students, conduction band. What is that conduction band I say? So conduction band, students, denoted by CB, you can call. So it is the range of energies considered by what I told you, conduction electrons, right? It is the range of energies considered by conduction electron, students. It is the range of energies considered by what, sir? Means conduction electrons. Okay. So what are the conduction electrons, sir? Means which are free electron, means which are completely free from the effect of the nucleus, right? Which are free electrons. Confirm? So this is the conduction band, students. So in between this valence band and conduction band and valence band, you know that one more is there, gap. That is called as a energy gap, students. So what is that energy gap that I can able to examine now? So third of that one now in the energy band diagram, that you can call energy gap, denoted by easy students. What is this energy gap, students? Sir, energy gap is the energy difference between what or means valence and conduction band. It is the energy difference between valence and conduction band. What is this energy gap indicate, sir? It always indicate how much is the energy, minimum energy required by an electron to move from valence to the conduction band. On jumping the electron from valence to conduction band, what is the required energy? That is defined by energy gap. Suppose if you don't apply that required energy, no electron can jump to the conduction band. So any electron can appear in the conduction band from valence band and applying the required energy. That required energy must be equal to energy gap. As long as you apply the energy less than energy gap, so none of the electron can go to the conduction band. When the electron can enter the conduction band, sir, and applying the required energy, that energy equal to what means at least equal to energy gap. Kanpana? So energy gap is the energy difference between valence and conduction bands, you can call. It always represent the minimum energy required by an electron to jump from valence to conduction band to become as a free. To become as what, sir? Free, you can call. And this energy gap is expressed in terms of the unit is electron volt, students. Virtually you know that unit for energy equal to joules. Here can able to use that work function formula. So that indicate electron volt. 1 electron volt equal to how much, sir? 1.6 into 10 power minus 19 joules. Confirm my option, students. And one more thing, so we can able to distinguish conductors, insulators and semiconductors just now I told based on what's the energy gap. So in the case of conductors, this energy gap is almost 0, students. If you go for insulators, the energy gap is too high. If you go for semiconductors, it's not 0, students. It's not very high. It's a moderate, small. Okay. So based on the energy gap, we can easily to distinguish conductor, insulator and what? Semiconductors. Confirm my option, students. Okay. What I told you, it is energy difference between conduction band and what? Valency band. Okay. It always represents the minimum energy required by an electron to become free on jumping from valence to conduction band. It represents minimum energy required by what, sir, means an electron to become free on jumping from where to where, students? Valence band to conduction band. So how much is the minimum energy required to jump from valence to conduction band to make that electron is free is denoted by energy gap. So this energy gap is expressed in terms of units what, sir, means electron volt. I told EC equal to EC minus EV, right? That to be exerted in terms of the unit is what, sir? Electron volt. What is that electron volt, sir? 1 EV. EV stands for what, sir? Electron volt, you can call. Work function formula I told students. 1 EV equal to how much means 1.6 into 10 power minus 19 joules. 1.6 into 10 power minus 19 joules. And so now the students, this one. So based on this energy band diagram, now I can able to distinguish conductor, insulator, and then I can able to go the required body of semiconductor. And so now, so because in a given atom, all the electrons not have the same energy, students, they have random values of energy. So how do you know the probability of energy in a given atom, sir? The range of energy considered by an electron in a given atom, how do you know, sir? That is known by the energy band diagram. It have 3 partitions I told: valence band, conduction band, and permittant gap. So it is the range of energy associated with the valence electrons which are not free. It is the range of energy associated with the conduction electrons which are 100% free. So how the electron can become free, sir? On jumping from valence to conduction band, it look like to be free. To jump that electron from valence to conduction band, how much is the minimum energy you require, sir? That is denoted by energy gap. So this energy gap size goes to be changing for conductor, insulator, and semiconductor, I told. Right. So now I can able to examine the first one of that one, sir, conductor. Okay. First of that one I can able to examine, students. Conductor I can discuss now. Conductors now I can able to examine. Sir, what is a conductor? It is one that can allow the electrons to pass through it very, very freely. What is a conductor, sir? Conductor is a body that can allow the electrons to pass through it very freely. Such type of materials are called conductors. Best example, I think that you know, students, metals. All metals are good conductors. All metals are what, sir? Good conductors we can call. Right? So, all metals are good conductors. You said that is copper, silver, gold. All these are the good metallic materials you can call. And in the case of conductors, the energy band diagram is such that in this case, the valence and conduction bands are superimposed, students. The valence and conduction bands are superimposed, indicating that in the case of conductors, the energy gap is almost to zero. That is negligible. See this one now. What is the energy band diagram here for particularly conductor materials? This one, I say. So this is Valency band, students. This is conduction band, students. Both are superimposed in this place. Right? Valence and conduction bands are superimposed, students. Like this. This is the superposition area, indicating that in the case of conductors, energy gap is almost to zero. That's the case. So what I told you, it is one that can allow the electrons to pass through it very freely. Okay, examples, metals, students. All metals are good conductors. What is the energy gap for this conductor, students? Zero. What is the meaning of this energy gap zero, students? Do you remember now? So even without any applied energy, the electrons look like to be act as a free. So for making the electrons free, I do not need to apply any external energy, students. All electrons are fundamentally free. They don't ask any external energy from you to make them as a free. Right? Because of their freeness, these electrons can easily wandering around valence and conduction bands without any extra energy. So all electrons are free, students. So these electrons can easy to move from valence to conduction band. At the same time, conduction to valence band. They are continuously circulating between valence and conduction bands, going to conduction band again, conduction to valence band without asking any extra energy. Such that you say that both valence and conduction bands are partially filled. So they don't stick on a single area, students. Continuously they move around valence to conduction, conduction to valence. Right? So suppose here the electrons are there, some of them go there, and immediately some other electrons are coming here. So it is continuously circulating around valence and conduction bands. They don't stick on in a single area. And you say that commonly in the case of semiconductors, whenever the electrons jump from valence to conduction band, you say that there is a loss of electron in valence band called a hole. Such type of holes do not be considered in the case of conductor. Sir, why don't you say that no hole in conductor means? The reason is what, sir? Even the electron jump to the conduction band, you don't say any loss of electron. So hole is considered by the loss of electron, sir. But in the case of conductors, even the electron jump to the conduction band, you don't say no loss. You don't say what, sir, means loss of electron. You don't say loss of electron. Why no loss of electrons, sir, means? The reason is that valence and conduction bands are superimposed together. Wherever the electron, it belongs to the same area. Whether the electron in conduction band or valence band, it belongs to the same place. So as long as you do not say that no loss of electron, under that condition, no meaning of hole. So when do you define the hole, sir? Whenever you say loss of electron. But even the electron jump to the conduction band, I don't say loss. Why, sir? Wherever it is belongs to the same area. Such that in the case of conductor, the current carriers are purely electrons only. No more other person. All electrons are free, even without any applied energy. Simple example, I take a copper wire. It have plenty of free electrons. Okay, right, sir, it have plenty of free electrons. No extra energy required to make them as a free. Already they are free. Suppose such type of copper wire I given to a fan or a tube light or any electronic device. Then current should be passing so that a fan or tube light may operate, sir, means. Sir, even conductor have a plenty of electrons. Without applied external source, none of the current can flow through the conducting wire. Sir, already they are free. They can able to move. By that movement, you know that current can be generated. Current equal to rate of flow of charge. So such type of copper wire I taken. that I apply to my electronic gadget like a fan or tube light or anything. Then why that electronic device do not operate until you don't switch on the supply means the problem here, students, conductor have plenty of electrons, but they don't have any restriction or controlling function. Based on that, these electrons in a given conductor can move randomly like this. Suppose this is a conductor, students, conducting wire. Confirm? I don't apply any source to this one, students. So all electrons are free inside the body, right? What I find out to means because of their freeness, they can move to travel in random directions, students. Some of them up, some of them down, left, right, like this. They choose to travel in any directions. So whatever electron in a given direction can generate the current, but polarity of current depending on the direction of flow. Upward electron generating some current, downward electron can generating some current, no problem. But they are moving in opposite direction means they have a opposite polarity. Like that left going electron generating current, right going electron also generating current. But because of their opposite direction, they have opposite polarity. So current by upward electron cancelled by downward. Current by left going cancelled by right going. So this type of unnecessary cancellations are more in a conductor without applied source because of random flow of electrons, all of them not flowing in a single direction, all of them flowing in different directions as they like at that time. So overall current may become zero or negligible, students. Sir, then what is the solution for this? What is the remedy for this? Remedy is only one thing, sir. Make them to move all in one direction. Make them to move all in what? One direction. How do you get that, sir? That to be done by some controlling function. That controlling function is called electric field, right? So this electric field make some electric force on that, and by that force all that electrons moving in one direction. So making all electrons to move in one direction with the applied electric field is called as a drift mechanism. That will be called what, sir? Drift mechanism you can call. So how do you make how do you get the electric field, sir? That is to be done by applied source like this. Suppose I apply a source here, some battery. Confirm, students? I apply some source of energy, battery. So with that applied source of energy of battery, if this is a positive potential, all electrons are attracted by positive potential like this. So the electrons are moving like this, right? All electrons are attracted by positive. So what are the electrons who are attracted by positive? They are repelled by negative, come like this. So instead of making a random direction of flow, now they can able to move in a single direction. They can able to move what, sir? In a single direction like this. This is the direction of flow of that now. So random flow of electrons can be converted into single direction of flow by this applied force, by applied field. That applied electric field done by the applied source. How do you know that one, sir? So electric field equal to potential per unit length, students. This one. So electrons are releasing from the surface. This become positive. The electrons are entering on the surface become negative charge. So now the electrons are moving in a single direction, they can produce the current, and the current by every electron should be additive, not be subtractive, because all are in the same direction, all are participating in current with the same polarity. This is the condition, students. So even conductor have a plenty of free electrons that require some source of external energy for drifting them in a single direction with applied electric field. That's the case. Confirm, students? Okay. So what I told you. So it is one that can allow the electrons to pass through it very freely, students. Example is metals. Who are current carriers here? Electrons only. The current carriers are what, sir? Electrons only. Don't say whole, students. Already I told you. Why, sir? Means even the electron go to the conduction band. So you don't say any loss of electron here. Confirm now? So current carriers are what, sir? Electrons only. What are the mechanism, students? Drift or diffusion? Drift mechanism. So drift mechanism is what, sir? Means making the carriers to move in a single direction and have an average velocity called drift velocity. Right? And due to their motion, you can able to generate a current called as a drift current, you can call, right? See this one now. The current carriers are electrons only, and current is due to what, sir? Drift mechanism, students. So under drift mechanism, right, the conductivity is possible with applied source or with applied electric field only. With applied source or with the applied electric field only. So the current carriers are electrons only, students, and current is due towards a drift mechanism. Current due to drift mechanism. Here valence and conduction bands are partially filled, students. Partially filled means, so none of them is completely filled, sir, because they are continuously circulating around valence and conduction band, right? Both valence band and conduction band are partially filled, sir. None of them is completely filled because, right, electrons are not stick on in a single area. They are continuously move around valence and conduction band, students. Understood now? Next one more, sir, students. Conductors can satisfy or can obey Ohm's law. Conductors can satisfy or obey Ohm's law, students. Sir, Ohm's law means immediately you know the word V equal to IR, where V stands for voltage, I stands for current, R stands for resistance, right? So, but that is the Ohm's law, no problem. But V equal to IR is the statement used to calculate the resistance of a body, R equal to V by I, right, in accordance with their voltage and current relation. Remember now, students, V equal to IR is the statement of Ohm's law applicable for both conducting and non-conducting materials. So for any material, you can able to use that formula V equal to IR, and using which you can able to define the resistance in accordance with the voltage and current relation. But one more Ohm's law is there that can be applicable only for conducting materials like conductors and semiconductor, students. So what that Ohm's law applicable for conductors means current density J proportional to E. That's the one, right? See this one now? What I told, students? Conductors can obey Ohm's law, okay, by which, what I say, sir, J proportional to E, students. J proportional to E. What is that J proportional to E, sir? Now I remove that one. J equal to sigma E. J equal to what, sir, written? Sigma E. What is that sigma, students? Sigma stands for conductivity. J equal to sigma E, students, where E equal to electric field, just now I told, with applied source electric field is considered. E equal to electric field, students, that equal to V by L. Unit is volt per meter, potential per unit length. So how much of the potential you applied per unit length, that to be called as electric field, right? What is that J, students? J stands for current to density. How much current that can be produced per unit area? The amount of current conductivity in unit area, that is I by A. Unit is ampere per meter square. Confirm? And what is that sigma, students? Sigma stands for conductivity. Proportionality factor you can call conductivity. Conductivity is a reciprocal of what's a resistivity. Okay, 1 by rho. Unit for this one is mho per meter, students. Mho per meter, or ohm meter inverse also you can write. So conductivity. So this is the formula of Ohm's law applicable only for conducting materials like conductors and semiconductors. It do not be applicable for insulator, students, because for insulator sigma equal to 0. Okay. So conductivity equal to reciprocal of resistivity. What is that resistivity, students? And resistivity, now I go, rho equal to 1 by sigma you can call, and it is expressed by using the Ohm's law as RA by L, students. Rho equal to RA by L, where R stands for resistance, A stands for area, L stands for length. So the resistivity of a body defined as R, rho equal to RA by L. So anybody can able to know the difference between resistance and resistivity, students? See, so now resistance depend on the nature of the material, physical dimensions, as well as temperature. Resistance depend on 3 factors, students. Physical dimensions, length, area, all this. Next, nature of the material. Next, temperature. Whereas resistivity is independent of dimensions, students. Resistivity look like a resistance, but it is independent of dimensions. Mainly depend on the nature of the material. For a given body, resistivity is standard 1. Convert now? So it is independent of dimensions. Simple example, student. Suppose I say that 2 bags are there. This is one bag. This is another bag. X, Y. So in each bag, apples are there. What is the cost of each apple means? I said 10 rupees. The cost of each apple, I say what sir means 10 rupees. In this bag, how many apples are there? 50. Here only 20 apples are there. What is the cost of this bag, sir? 500. What is the cost of this one, sir? 200. So each bag containing only apples, but the cost is different because quantity is different. Here more quantity 50, here less quantity 20. So the cost is different. That's called resistance. So why more quantity means? Because bag dimensions may be more. Here why the less quantity means? Bag dimensions is less. But what is the cost of each apple in any bag? The cost of each apple in any bag should be same. That is 10 rupees. So it is independent of the dimensions of the bag. This is called resistivity, students. So resistivity is nothing but a resistance only, but calculated in unit dimensions. So based on that, resistivity must be independent of dimensions. Resistivity must be what, sir? Independent of dimensions. Whereas resistance depend on dimensions, students. Suppose if you take a gold wire, heat that one now. Whenever I heat that gold wire, so dimensions are changing. So that whose resistance changing. But before heating, after heating, what is the resistivity mean? That should be same, because it's even after heating the gold wire, it's not be a silver wire. It should be same as a gold. Only dimensions are changing, resistance changing, but resistivity not be changing. So resistivity and resistance main difference is what, sir? Resistivity is independent of dimensions, depend on the nature of the body. Whereas resistance depend on the nature of the body as well as dimensions you can call. That's the importance. Okay. So what is this resistivity for conductor, students? The resistivity of these conductors is around 10 power minus 8 or 10 power minus 7 ohm meter, students. Conductors resistivity is very, very less, which is about 10 power minus 8 ohm meter. Confirm all these things, students? Okay. So conductors can obey Ohm's law, you can call. Conductors can obey Ohm's law, students. This is the case. And one more thing, students, conductors have positive temperature coefficient of resistance. Conductors have what, sir? Positive temperature coefficient of resistance. I told that resistance not only depend on dimensions and the nature of the body, resistance of the body can also depend on the temperature, I told. So with respect to temperature also, you may find out some variations in the resistance, I say. So what the thing I told, sir? Conductors have positive temperature coefficient of resistance. Positive temperature coefficient of resistance means as the temperature increases, the resistance of conductors increases. Confirm now? Conductors have positive temperature coefficient of resistance. Confirm now, students? Conductors have what? Positive temperature coefficient of resistance. What is the meaning of that one I told you? R proportional to T. As the temperature increases, resistance of the conductor increases. So in conductor, current carriers are only electrons, no meaning of hole. In conductor, current mechanism is a drift. So once again, you discuss later what is the drift condition. I think that you know FET and MOSFET in which the conductivity only by drift mechanism. Okay. Other than that, a conductor can obey Ohm's law, by means of which I told the formula J equal to sigma E. Sigma stands for conductivity, reciprocal of resistivity. So conductors have positive temperature coefficient of resistance, I told. Temperature increases, the resistance of conductor increases. Confirm now, students? Now I can able to check out the next one of that is insulator. I go for insulator, students. So as compared to conductor, insulator is simply called non-conductor, students. So it is a body of non-conductor, quite opposite to conductor. What means? A insulator is a body that do not allow the electrons to pass through it freely. An insulator is a body that do not allow the electrons to pass through it freely. Best example, right? Air, paper, plastic, rubber, diamond, all these things. Right? These are the good insulators, you say. Okay, insulator is a body that do not allow the electrons to pass through it freely. And if you go for energy band diagram for insulator, so here valence and conduction bands are separated by very high energy gap. Suppose if you go for a diamond, students, in the case of diamond, the energy gap is around 6 electron volt, you can call. So energy gap is too high. In the case of conductors, I told energy gap is almost 0, but in the case of insulator, the energy gap is too high, around 6 electron volt, students, like this. This is the case, students. This is the valency band. This will be the conduction band, So these together separated by energy gap, that should be very high, students. That should be very, very high. So under normal condition, none of the electron may jump into the conduction band. Under normal condition, no electron can jump from valence to the conduction band, such that all electrons belongs to the valency band. So that valence band is completely filled, conduction band is completely empty under normal condition. So no conduction electron means none of the electron is free, such that current is 0, you can call. Current is 0. So current 0 means resistance look like be infinity using Ohm's law, R equal to V by I. And if you apply very high energy like this, students, if I apply very high energy, very, very few electrons can become free and causing a negligible current. Such current is of no use. Confirm now? Suppose if I go to apply higher energy like this, students, originally you don't apply. If I go to apply such energy, you may find very, very few electrons to be free, and that electrons not causing a required conductivity, students. That is a very useless conductivity. Such that commonly insulator is called as a non-conductor. Insulator is commonly called as a non-conductor, you can call. Right, no current carrier, no current mechanism. And one more thing, sir, the insulator have negative temperature coefficient of resistance. I told conductors have positive temperature coefficient of resistance, but insulators have negative temperature coefficient of resistance, students. Means as the temperature increases, the resistance goes to be decreases. That's the case. Okay. So for insulators, you don't apply the Ohm's law of J equal to sigma E. So now, students, what that insulator I told? It is a non-conductor, I told, students, that do not allow the electrons to pass through it. Okay. Example, air, paper, plastic, all dielectric materials, paper, plastic, diamond, all these things. Confirm? I told you, sir, energy gap is very high. Okay. Under normal condition, what I told, students? Under normal condition, no electron is free. That is, conduction band is empty. That is what you can call conduction band is empty, students. Conduction band is empty, you can call. So it is no current, sir, no current mechanism, I told. Conduction band is empty means none of the conductivity is there. Right? And I told, sir, it can have what I told you, negative temperature coefficient of resistance. It has negative temperature coefficient of resistance. Negative temperature coefficient of what's resistance. What is the meaning of that one, sir? R proportional to 1 by T. R proportional to what, sir? 1 by T. As the temperature increases, resistance decreases. As the temperature increases, the resistance goes to be decreases, students. So this is about what, sir, means insulator. So insulator is a body that do not allow the electrons to pass through it freely. Insulator is a body that do not allow the electrons to pass through it freely. Simply it is a non-conductor, I can call. According to the structure, energy gap look like to be very high, students. Best example, diamond. If you go for a diamond, the energy gap is about 6 electron volt, I can call. Because of high energy gap, more energy required to make electron free. Such energy you don't apply, students. Because of this, none of the electron is available in the conduction band. All belongs to only valence band. So conduction band is empty. So no current carrier, no current mechanism. So simply it is called non-conductor. Right? Ideally current zero, resistance will be infinite. Under application of very high energy, you may find a very, very small number of electrons to be free and causing a negligible or useless current. So that resistance look like to be very, very high instead of infinite. Okay, so based on that, it have a negative temperature coefficient of resistance. That is what I told, sir. R proportional to 1 by T. As the temperature increases, the resistance decreases. Now I can able to go my required person. That should be called what's a semiconductor. Check out now the students, semiconductors. Now I can able to examine students semiconductors. What is a semiconductor? A semiconductor is a body whose electrical conductivity lies in between conductor and insulator. A semiconductor is a body whose electrical conductivity is in between conductor and insulator. That to be called as a semiconductor. Confirm now? So in the case of semiconductor, the electrical conductivity is more as compared to insulator and less as compared to conductor. Confirm now, students? Okay, what I told you, its electrical conductivity is in between conductor and insulator, I told. Okay, its electrical conductivity lies between conductor and insulator, students. Its electrical conductivity lies between conductor and what? Insulator. That is, conductivity of a semiconductor greater than insulator, but less than conductor, students. So whose conductivity more as compared to insulator, less than conductor you can call. So whose electrical behavior in between conductor and insulator, students. As compared to conductors and insulators, energy gap is moderate, small. In the case of conductors, energy gap almost zero. In the case of insulators, energy gap is too high, you can call. But here, not much high, not zero, sir. It is a moderate, very small. Around 1 electron volt you can call. Right, students? Energy gap is a small. Energy gap is a small. See this one now. What is this, students? This is the case, you can say. So this is by the Valency band, students. This will be the conduction band, you can call. So this is the energy gap I told student, that is a small. Energy gap should be small for this. So anyhow some energy gap is there, not zero like conductors. What the thing? So without any applied energy, students, without any applied energy, right? None of the electron can be in the conduction band. No electron can jump from valence to the conduction band. So that no electron is available in the conduction band means it look like an insulator. So simply remember, a semiconductor without applied source, right, where no electron is free and look like act as an insulator. Look like act as a insulator, students. On applying the energy, so this is should be applicable energy, students. This should be applicable energy, not much high. So it should be applicable around 1 electron volt only, I told. So on applying the required energy, so what is the electron in the Valency band who got a required energy may jump to the conduction band, students, may jump into the conduction band like this. So on applying that required energy, the electron in the conduction band may jump to the valence, while the electron in the Valency band may jump to the conduction band and become as a free. So on jumping the electron from valence to the conduction band that look like be free, you can call, you may find some loss of electrons, students. Sir, you don't say loss in conductors. Why you say here means, I told there in conductors, even the electron jump into the conduction band, low loss, because they are superimposed there. They are considered as a single area now in the case of conductors. But in the case of semiconductors, they are not superimposed, sir. They are separated areas. So completely they are separated by energy gap. So whenever the electron can jump, then according to the law of conservation of charge, you may find a loss of electron. So that loss of electron in the valence band causing an empty area. That empty place should be called as a hole. This is the hole, students. So hole is the vacancy. Hole is the vacancy due to removal of electron from valence to the conduction band. According to the law of conservation of charge, it is due to the removal of electron such that it must be a positive carrier. Electron is a negative charged particle. So on removal of negative charged particle, you must and should get positive charged particle. Right? So hole must be a positive charged particle. What is the charge of hole, sir? Same as electron. That is 1.6 into 10 power minus 19 coulombs. Understand, students? And now, even the hole in valency band, students, what are the hole in valency band? For that, no binding restrictions. So, hole look like be free. Sir, in valency band, you remember now, the binding restrictions only for electrons, never for hole. Hole is a guest person in that place. Confirm? So, even the hole in valency band, it should be a free carrier. It should be what, sir? Free carrier. So, who are the free carriers in the case of semiconductors, sir? Electrons in conduction band and holes in valency band. Electrons in conduction band and holes in valency band. These are the free carriers. They can participate in current conduction. They can participate in current conduction, students. Okay. And one more thing you remember here. What is the electron who enter the conduction band? Is it stay permanently there? Means not. Understand my option, students? And jumping to the conduction band, what is the electron can spend in the conduction band only for a certain finite time. Don't say permanently. Sir, how much time that can you say, sir? That to be called as a lifetime, carrier lifetime denoted by tau. Lifetime is an approximate one, average one only, not by fixed one. So, what is the lifetime it have? Once it can reach that concerned lifetime, what the electron, sir? The electron can return to the, what sir means? The electron should be returned, sir. That electron to be returned from conduction to the valence band, sir, like this. And then collide with the hole. And so now my option, students, and jumping the electron to the conduction band, it look like a free and can stay in that place only for a particular, what that means, finite time. That's not a fixed one. That's an average time called lifetime, students. Once that time is happen, what I told you, that electron return to the valence band and collide with the hole, sir. That recapturing of electron and hole together is called as a recombination, students. Right? Recombination process. Confirm my option. So the capturing of electron and hole together is called as a recombination, students. Right? This recombination of electron and hole radiates some energy, students. Radiates some energy. What is the radiation of energy, sir? That is depending on the type of semiconductor. So based on the band gap, there are two types of semiconductors, sir. One is a direct band gap semiconductor. Other one is a indirect band gap semiconductor. In the case of direct band gap semiconductor, the recombination process can radiate light energy, students. In the case of indirect band gap semiconductor, the recombination process can radiate current conductivity, students. And my option, in the case of direct band gap, the radiation can, the recombination can radiate light conductivity, whereas in indirect band gap, the recombination can radiate current conductivity. And not only that one, students, already I told that it is a vacancy. Into that vacancy, again electron comes, means that place is again be filled with valence electron, like this. So again, the electron can be filled into that place. So your electron get back, and due to recombination process, extra you can get conductivity. So it is a continuous process in the case of semiconductor, as long as you can apply the source of energy. So continuous movement of carriers from valence to conduction band, and then they returned back and recombine the hole and regenerate the valence electron again, and due to the recombination process, they can able to radiate the energy. So this radiation of energy to be light conductivity in direct band gap semiconductor and current conductivity in the case of indirect band gap semiconductor. Sir, who are the direct band gap? Who are the indirect band gap semiconductor means? So in the case of direct band gap semiconductor, simply remember, students, I don't go in depth. So simple logic I say. In the case of direct band gap semiconductor, the momentum of carrier in valence and conduction band same. Means the carrier can move from valence to conduction band without any changing momentum. No need to change the momentum, sir. So what is the electron? Right, in conduction and valence band can able to move from valence to conduction band with the same momentum without changing momentum, I can call. That's called direct band gap. Best examples are gallium arsenide, gallium nitride, gallium phosphide, all this. Right. So there was phosphorus materials or fluorescent materials. Next, indirect band gap semiconductor, quite opposite. In the case of indirect band gap semiconductors, what are that momentum of electron in valence and conduction band not be same. So they can move from valence to conduction or conduction to valence band with a changing momentum, sir. Momentum of electron not be same in valence and conduction band in indirect band gap semiconductor. Best example is germanium and silicon. Best example is what, sir? Germanium and silicon. Confirm now, students? Sir, you may ask one more thing. Sir, here you say that electron jumping to the conduction band, you are getting a hole, no problem. But here electron is returned to valence band. At that time, again you get a loss here, means, sir, it is the only visiting area for electron. What is the permanent area for electron? Means only valence band. Whenever they skip from permanent area to the other area, at that time only you can able to generate a loss. So what is the electron here? Even it is returned to the conduction valence band, you don't say loss there. Confirm my option. So that holes never be considered in conduction band, sir. Holes always be considered in valence band only. Such that in a semiconductor, the current carriers are electrons in conduction band and holes in valence band. Understand the story, students? Okay, check out this. Without applied energy, okay, no electron is free, I call, and act like insulator. Confirm now, students? So a semiconductor act as an insulator without applied source. Okay. With applied energy of required, okay, electron can become free. Confirm. And removal of electron in valency band represent, what I say, students? Hole. Removal of electron in valence band represent what, sir? Means hole. What I told you, hole is a vacancy due to the removal of electron. I told students, hole is a vacancy due to the removal of electron. Hole is a vacancy due to removal of electron from where to where, students? Valence band to conduction band. Answer my option, students. Hole is a vacancy due to removal of electron from where to where? Right? Removal of electron from valence band to conduction band, you can call. Right? Hole is what, sir? Positive carrier or negative carrier? Hole is a positive carrier of charge, positive carrier of charge 1.6 into 10 power minus 19 coulombs. Confirm now? So current carriers are, who are current carriers here? Electrons in conduction band. Confirm now, students? Electrons in conduction band and holes in valency band. Holes in what, sir? Valency band, you can call. So what are the electron who stay in the conduction band only for certain time, students? That is called as a lifetime. That lifetime is not fixed, I told you. After that, it can return to the valency band and what, sir, means collide with the electron. That process is called what, sir, means recombination. Confirm now, students? So that recombination process can radiate either light conductivity or current conductivity, I told. Confirm now? See this one now? Electron can stay in conduction band for a certain finite time called lifetime, students. So that lifetime not be fixed one. Look like our human being lifespan. So can you fix your lifespan? So commonly you say that nowadays the average human lifespan is 60 years. Can you say that each and every person exactly can stay on this earth surface for 60 years? Means not like that. An average you say, like that here also same. So this is an average time only, not be a fixed time, students. An average the carrier can spend in the conduction band for certain time is lifetime tau, right? And then return to valency band and collide with hole to regenerate the valence electron again. Confirm now, students? So it can collide with the hole and thereby regenerate that valence electron again. So that collision of electron and hole to be called as a what, sir? Recombination, I told. Okay. The collision or right. of electron and hole is called, what I said students, recombination. Right? Recombination you say. So the recombination of electrons and holes can radiate, which can radiate what, sir? Either light or current conductivity, students. So that is depending on the type of band gap, students. So depending on the type of band gap, you know that indirect band gap and direct band gap you say. Okay, depending on the type of band gap, we have direct and indirect band gap semiconductors, right students? We have direct and indirect band gap semiconductor, students. So what I told means, in direct band gap, okay, the momentum of electron is the same in valence band and conduction band. Right, carriers can able to move without changing momentum, students. Electron momentum is the same in valence and conduction band, and in which, okay, recombination can radiate what? Light conductivity, students. Recombination can radiate what, sir? Light conductivity. Example, what do you know, sir? Gallium arsenide, gallium phosphide. So all these things, students, used in, I think that you know, one of the diode, LED, light emitting diodes, lasers, all these are the cases. Light emitting diode, all these things, so direct band gap semiconductor may use there. And understand now, students. One more is, what sir means? Indirect band gap semiconductor you can call. In indirect band gap semiconductor, students, okay, the momentum of electron is not same in valence band and conduction band. So it is moving with the changing momentum, students, okay, where the recombination can radiate current conductivity, students. So heat or current conductivity conditions there. Heat or current conductivity concepts. Example, you know, the most popular semiconductor you may use, germanium and silicon. The most popular semiconductors may use, students, germanium and silicon, right? That's a indirect band gap semiconductor, right? So depending on the type of band gap, I told the indirect band gap and direct band gap semiconductor, students, okay? So in the case of semiconductor, the current carriers are, both are there. Those are electrons in conduction band and holes in valency band. Understand the students these things? Next, again, you discuss this. One more of the important thing in the case of semiconductor, students, the energy gap of semiconductors decreases as the temperature increases. One of the important thing, energy gap of semiconductor decreases as temperature increases. Energy gap of semiconductor decreases as temperature increases. So energy gap decreases means then required energy for making the electrons to jump into the conduction band decreases, so that the conductivity increases. So with increase of temperature, energy gap decreases means required energy decreases to make the electron free. So that as the temperature increasing, required energy decreases means automatically the conductivity goes to be increases, students, right? That's the importance of this. So most commonly used semiconductors are germanium and silicon, you know. What is the energy gap of germanium, students? That is around 0.72 electron volt for germanium and 1.1 or 1.12 electron volt for silicon at room temperature of 300 degree Kelvin, students. At room temperature of 300 degree Kelvin, this is the case. Confirm my option. And semiconductor have negative temperature coefficient of resistance due to this. So as temperature increasing, energy gap decreases means conductivity increases, so that resistance decreases, you can call. So it has a negative temperature coefficient of resistance. Negative temperature coefficient of resistance, students. So it is a person that has negative temperature coefficient of resistance. That is what I told you, R proportional to 1 by T, students. R proportional to 1 by T. But practically you remember that in a semiconductor, the resistance is decreasing exponentially with the temperature. Resistance is decreasing exponentially with the temperature, right? In a semiconductor, resistance decreasing exponentially with temperature, students. Okay? Resistance decreasing exponentially with the temperature, you can call. So if you write mathematically means, this one you can write. What is that one means? R equal to x into e power minus y by t ohms. Where x and y are constant, students. X and y are what? Constants. Okay. R equal to x into e power minus y by t. Resistance of a semiconductor decreasing exponentially, that is rapidly with the temperature. So resistance of a semiconductor, minus for decreasing, students. E for exponential means rapidly with the temperature, you can call. Understood on this? So this is about the semiconductors, you can call. So the resistance of a semiconductor decreasing very rapidly with the increase in temperature, students. It have a negative temperature coefficient of resistance. The most popular semiconductors, you know, germanium and silicon, whose energy gaps I discussed, 0.72 electron volt for germanium, 1.12 electron volt for silicon, that to be discussed at a room temperature of what? 300 degree Kelvin. Okay. Now I can able to go for types of semiconductor, students. Just I indicated that basic condition of semiconductor. Now I can able to go for the types of semiconductor. Confirm my options this. So in a semiconductor, who are the current carriers, sir? Both electrons and holes. Electrons are the carriers in conduction band, holes are the carriers in valence band. How to get a hole, student? Hole can be generated by replace of electron from valence to conduction band. Simply you say hole is a vacancy. So what is the electron? Is it permanent in conduction band? Never. It can stay only certain time called lifetime, then return back to valence band to collide with the hole and regenerate the electron again. But anyhow, this collision process called recombination can radiate current or light conductivity, I told. Remember this, students? So the generation and recombination of these electrons and holes is a continuous process in a semiconductor with the applied energy source. With the applied energy source, generation means generating the electrons as a carriers in conduction band. And recombination means return the electron and recombine the hole. So it is a cyclic process continuously as long as the source is applied. That's the case, students. Okay. Now I can able to examine the types of semiconductors now. I can go to discuss the types of semiconductor, students. Types of semiconductors, now I go. I can go into discuss what that means, some types of semiconductor, students. So you may find out mainly two types of semiconductors. One is an intrinsic semiconductor, other one is what you can call, sir, extrinsic semiconductor. How many types of semiconductors are there? Two types of semiconductors are there, students. One is intrinsic, other one is what you can call extrinsic, you say. So this is the intrinsic, other one is extrinsic, students. So first one of that one I can able to discuss, students. First of that I can go to discuss intrinsic semiconductor. First one of that one I discuss, students, intrinsic semiconductor. So an intrinsic semiconductor is called as a pure semiconductor. What is the pure semiconductor, sir? A semiconductor without any added impurity is called pure semiconductor. A semiconductor without any added impurity is called as a pure semiconductor. Okay. So many pure semiconductors are there. but I don't want all that. Based on my conductivity, I consider the pure semiconductors are germanium and silicon. So these are the pure semiconductor students, right? And once again, if you compare germanium to silicon, sir, who is mostly preferred for conductivity among those two means silicon as compared to germanium. Why, sir? You can examine. Originally, if I compare germanium device and silicon device with the same applied source, in which the conductivity more students, in germanium device, the conductivity more than compared to the silicon device on applying the same source of energy. And so my option, students, same dimensions. What are the germanium device dimension, silicon device dimension, both are same and applied with the same energies. Then who can have more conductivity than others, sir? I told that germanium device have more conductivity than compared to silicon. But even the conductivity is more in germanium, you don't prefer germanium. You are preferring only silicon, even the conductivity is less. What is the main reason to use silicon than compared to germanium, students? Remember now, Kamal asked in interviews. First one, silicon should be available very freely in the nature, abundant. Silicon should be available very freely in the nature, students. Next, what that one means? In silicon body, the minority carrier effect is less than compared to germanium. So that silicon made material is quite stable than compared to germanium made material. So minority carrier effect is very less in silicon body than compared to germanium, students. So based on that, what I can say, silicon body is more stable than compared to germanium. This is one more. Next, as compared to germanium, a silicon made body to be operate even at high temperature. So who to be maintaining the conductivity even at operate at high temperature means silicon. See, for now, students, one of the term is there called critical temperature. So the critical temperature for germanium body is about 85 degrees centigrade. For silicon body, it is about 200 degrees centigrade, right? So at 85 degrees centigrade, so germanium made device can be applicable to use up to 85 degrees centigrade only. Whereas if I go for silicon made body, that will be useful up to 200 degrees centigrade. So these are the practical reasons to use silicon than compared to germanium. Sir, why the silicon have a less conductivity than compared to germanium means, according to the fundamental condition, a silicon body have more resistivity than compared to germanium. By that, the conductivity of silicon is less. Why the silicon body have less conductivity means because of its high resistivity than compared to germanium. So even conductivity is less, so that's not a problem. So most preferable thing in the case of your semiconductor appliances is nothing but silicon made devices. Even you know that in IC technology, so IC is made by purely by silicon, not by germanium. Confirm, sir? So first I can examine the intrinsic semiconductor, students. So an intrinsic semiconductor is a pure semiconductor without any added impurity. Best examples are germanium and silicon. Confirm my option? Okay. It is a pure semiconductor without any added impurity, students. Without any added impurity, it is a pure semiconductor, you can call, right? So best example I told you, germanium and silicon, sir. Germanium and silicon. So whenever you can compare germanium and silicon, mostly preferred is only silicon, I told. Live with that one. Remember now, according to the electronic configuration of Bohr atomic model, germanium and silicon are tetravalent atom, students. Tetravalent means they each have 4 valence electrons in their outermost cell. Confirm, students? Each atom have 4 valence electrons in their outermost cell. See, so now, according to the Bohr atomic model, an atom look like to be stable atom if it has a minimum of 8 electrons in the outermost, students. So an atom to be stable, if it is either outermost cell is completely filled, and if not possible, it must and should need a minimum of 8 electrons, students. An atom look like to be stable if it has a minimum of 8 electrons in its outermost cell, students. So, but I told that germanium and silicon are tetravalent. I told each can have how many electrons in their outermost cell? 4. So to make that concerned atom to be stable, you need 4 more electrons to each atom. So originally I need a minimum of 8 electrons to make that outermost cell is to be somewhat stable now. Okay, an atom to be stable by having a minimum of 8 electrons in the outermost, I call. But each germanium or silicon atom having only 4 electrons in the outermost. So that each atom may need how many more? 4 more. How to get that 4 more electrons, sir? Means that to be done by the bonding. That to be done by what, sir? Bonding. So what is the bonding, sir? Means bonding the right. Bonding is nothing but the meaning of attraction or repulsion between 2 or more neighbor atoms. By that you can able to carry the electrons from one to the another atom. So bonding is the mutual understanding between the atom, students. It is the mutual understanding between the atoms. By that the electrons can be transferred or saved from one atom to another atom to make that concerned atom as a stable. To make that concerned atom as a stable. Right. So what are the conductors? Uses metallic bond, students. Insulators uses ionic bond, students. Semiconductors, now you discuss that can able to use covalent bond. Confirm my option. So conductors uses metallic bond, insulators uses ionic bond, semiconductors uses what, sir? Covalent bond. I told students. My required topic is semiconductors. So semiconductor uses what, sir? Covalent bond. Right? What is that covalent bond? Now can able to examine. And so now my option, students. Germanium silicon are what? Tetravalent. So which are what I said? Tetravalent, students. Which are tetravalent I call. Right? And each have how many electrons? 4 valence electrons. So according to the Bohr proposed model, an atom may need minimum of 8 electrons in the outermost. So that each require how many more electrons? 4 more electrons. Right? So that each atom require 4 more electrons. Confirm? To become stable. And is done by what I told, students? Bonding. So bonding is the mutual understanding between 2 or more neighbor atoms. So to keep that concerned atom as a stable by transferring the electrons. And is done by what type of bond I use in semiconductors? And is done by covalent bond. What is the covalent bond? I discuss first. Confirm now? Sir, what is the covalent bond? A covalent bond is one that can be obtained by sharing one electron from a neighbor atom. So every bonding can able to share only the electrons only. But covalent bond have some restrictions, sir. What type of restrictions? Means covalent bond is obtained by sharing one electron from a neighbor atom. Neighbor atom may be any type, sir, either similar atom or different atom, no restrictions. So neighbor atom may be same type or different type, for that no restrictions, right? But every neighbor atom can give only one electron, not more than one. Suppose I need 4 electrons. These 4 electrons you may get from 4 neighbor atoms, not from single neighbor atom. So what are the required 4 electrons I told for germanium or silicon, right? That required 4 electrons you may get from 4 neighbor atoms of any type of similar or different. But every neighbor atom only give 1 electron. That's a condition. And not only that, sir, one more condition also there. What is that one means? That neighbor atom not be in a random position. That neighbor atom must be in a symmetric position so that it can satisfy crystalline structure. Confirm my option, students? So from a neighbor atom it can share only 1 electron, and that neighbor atom not be in random place. That neighbor atom must be in a symmetric position. Confirm my option, students? So covalent bond structure look like a crystalline pattern. Sir, depending on the atomic structure, you know that 2 type of patterns are there: crystalline pattern and amorphous pattern, students. In crystalline structure, the arrangement of atoms must be in a symmetric order, not in a zigzag order. Suppose if you go for amorphous, students, in amorphous body, what sir means? The arrangement of atoms in a zigzag manner. What is the best example of crystalline structure, sir? Conductors. What is the best example for amorphous conditions, sir? Insulators. So understand, students, crystalline structure have symmetric pattern of atoms. So the arrangement of atoms in a regular or symmetric order. And amorphous is what, sir? In the case of arrangement of atoms is unsymmetric or zigzag manner, random manner. Best example for crystalline is what, sir, means? Conductors. Best example for amorphous is insulator. So to behave like a conductor, the semiconductors uses covalent bond which must be crystalline structure. Which must be what, sir? Crystalline structure. Understood my option, students? So semiconductors uses covalent bond that is done by sharing of 1 electron from a neighbor atom. That neighbor atom may be any type I told, and which must be in symmetric position, look, to behave like a crystal, to behave like a crystalline structure. Suppose I can able to do that silicon crystal structure, students, pure silicon crystal structure. See this one now. This is a silicon crystal structure, students. Just I take some part of silicon crystal. Confirm. This is a silicon crystal, students. All are silicon atoms, I say. Everything is a silicon atom. Right? All these are silicon atoms. Understood now, students? Everything to be a silicon atom. Okay. So each silicon atom is a tetravalent, I told, having how many valence electrons? 4 valence electrons. Confirm? Each can have 4 valence electrons, students. Now I indicated that. This one. This is that one, students. So I indicate that like this means that is a valence electron attached with that parent atom. That is a binded electron. In our language, that electron belongs to the valency band. That electron belongs to valency band, student. Like that, every atom have 4 valence electrons you can call. Like this. Understood, students? Every atom have how many valence electrons? 4 valence electrons. Confirm? So this is the case. So I indicated for every silicon atom, right? 4 valence electrons like this. So that electron belongs to the valency band, I say. Confirm now, sir? I indicated this. How to get the covalent band? Covalent band is the process of sharing of one electron from a neighbor atom. That neighbor atom may be any type, I told, students. That neighbor atom may be any type, I told. Right? But must be in symmetric position, I told. Check up now. For this atom, I found the bonding. So I need 4 electrons, sir. So already 4 electrons are there. According to the Bohr proposed model, 4 more electrons are required to make as a stable. Right? So now I can able to go, students. One of the electron I can able to share from this atom. It is a symmetric position to it. So this combination is called as a covalent bond, and each covalent bond containing 2 electrons, that is called as an electron pair. Sir, can I share one more electron from the same atom? Means not possible. I told that each supporting neighbor atom give up only 1 electron, never more than 1. So whose contribution is over, you don't have a chance to get 1 more electron from the same atom. So you can try from another atom. Okay. Sir, can I get from this one? Means it's not possible because it is a random. So can I get from this one? Means yes, it is possible. You can get. Sir, can I get one more also from the same? Means not possible. Over. So like that you can able to get 1 more from this. You can get 1 more from this. So 4 symmetric neighbor atoms are there. So from 4 symmetric neighbor atoms I can get 4 electrons such that this concerned central person is a stable. Sir, why do you take all our silicon? Means because I consider that intrinsic semiconductor, it is a pure semiconductor without doping, so that all are silicon atoms only. Right? You can take either pure germanium or pure silicon. Suppose I consider that pure silicon. So central atom I can provide that required 4 electrons, so it is a stable. So I do this job continuously for all other atoms also. Can I do it now? So it is possible. It is possible. It is possible. It is possible like this. Okay, sir? This is the case. So I done that covalent bond structure. So even I finish this covalent bond structure, you observe now in this structure, students, only this fellow is stable, not all. According to the structure you drawn, only this fellow is stable, sir, not all things. What are that suppose neighbor atom, other one, sir, means you do not complete that one, it requires 2 more electrons. It requires 1 more, it requires 2 more, 1 more, 2 more, 1 more, 2 more. So they are searching for some neighbor atoms again. So the covalent bond process is a continuous process, no end condition. So it is a cumulative process, continuous process. You don't find any end in the covalent bond. What's my option, students? You don't find any end in the covalent bond. It is a continuous process, you can call. It is a continuous process. Confirm my option? So covalent bond structure is a cumulative, and as well as it is a crystalline structure. Cumulative means continuous process. Understand the students? Okay. What I told you. So done by what, sir? Covalent bond you discussed. How to get a covalent bond, student, I told. Covalent bond is obtained by sharing an electron from neighbor atom, okay, that may be any type I told, which is in symmetric position to it I told. Confirm? Which is in a symmetric position to it. So covalent bond represent a crystalline structure, sir. Covalent bond is a crystalline. See this for now. Anywhere the arrangement of atoms should be symmetric, regular pattern, not be irregular. Covalent bond is a crystalline structure, students. Okay. And is a cumulative. Cumulative means continuous, students. You don't find any end. It is a cumulative bonding. Okay. It is a cumulative. So this is a covalent bond, students. Every covalent bond containing electron pair. Every covalent bond containing electron pair, students. So this is the structure. Sir, to this structure, suppose I don't apply any energy source. I don't apply any energy source. Without any applied energy source, no electron is a free, students. Without any applied energy source, no electron is a free, students. No electron is free means it look like to be act as an insulator. Okay, when do you get the electron free, sir? By breaking the covalent bond. How do you get the electron free, sir? By breaking the covalent bond. How to break the covalent bond, sir? Applying the required energy. What is the required energy, sir? That required energy equal to energy gap. Sir, it is interrelated with the energy band diagram. So this is the valency band. This is the conduction band I call. Confirm now, students. I don't apply any energy source. Without any applied energy source, all electrons are belong to the valency band. All electrons are belong to what, sir? Valency band you can call. Sir, how do you make the electron to be free? So the electron should become free only on breaking a covalent bond. On breaking a what, sir? Covalent bond. Sir, how to break a covalent bond? Covalent bond should be break up by applying the required energy. That required energy equal to energy gap. And I told that at room temperature for silicon body, this energy gap equal to 1.12 electron volt. So on applying the energy source, that energy distributed to all the covalent bonds in the crystal. So that energy commonly you can call it the thermal energy, students. Because with applied source, the temperature of the body increasing, so it is called as a thermal energy. It is called as a thermal energy, students. Denoted mathematical as a kT electron volt, where K stands for Boltzmann constant, T stands for temperature in degree Kelvin. So with the applied energy source, right, the heat can be generated by that. The applied source to be expressed as a function of temperature called as a thermal energy can call using work function condition. So this energy to be distributed to every covalent bond in the crystal, not be of the same order. At a given time, one covalent bond may get more energy than other, but energy to be distributed to every covalent bond, every bond in that crystal. Every covalent bond to which the energy distributed in that crystal. At a given time, what are the covalent bond who got a required energy that can able to break up? Confirm my option, students. With applied energy, so the energy to be distributed to every covalent bond in the crystal, but not be of the same order. At a given time, one bond may get more energy than other. So no problem, but every bond can be able to get the energy from source. At a given time, what are the covalent bond who got a required energy that can able to break up? That can able to be what? Break up. So what is the required energy? That required energy equal to energy gap. That energy gap equal to how much? 1.12 electron volt I told. For silicon. 1.12 electron volt for, sir, silicon crystal. Suppose I take an example, students. Sir, among this covalent bond structure, one of the covalent bond got a required energy. I assume that this is the covalent bond who got a required energy I told. So it can able to get break up. It can get break up, students. Sir, on breaking a covalent bond, whatever the two electrons, is both electrons are come out as a free, or one of them come out as a free, or none of them come out as a free means, sir, among that electron pair of two electrons, only one have a chance to come out as a free, sir. Even a covalent bond broken, you never say that both electrons to come free. Why, sir? If both electrons are come to be free there, so inside the bond, you may get holes only. Two holes never form the bonding. Why, sir? Already I told that for hole no bond structure. So right, even the hole in the valency band, for that no binding restrictions I can call. Only binding restrictions or bond conditions considered only for electron. So to keep that bond continue, so among the electron pair, only one electron have a chance to come out as a free. That may be either X or Y. Don't say both. Understand, my students? Okay. So if both electrons come out as a free, under that condition inside the bond, you may find only two holes. With respect to holes, bonding is not there. Bond considered to be associated with the electron only, never with the hole. So among the two electrons, only one have a chance to come out as a free, sir. Never be both. Suppose either X or Y. Suppose I say that, sir. Suppose this is come out, I can call. So this is come out, I can call. So this is coming out, sir. That can be out. So that electron is here, sir. That is called a free electron. Right? So in our language, that is this free electron. Sir, both are same. Energy band diagram, covalent bond structure should be same. Here, what do you say, sir? Loss of electron or not? Loss of electron. How do you express the loss of electron? Hole. So on jumping the electron to the conduction band, you represent a hole. So that hole to be created here. So the removal of electron inside the bond represent a hole. And this is now the bond condition. So this is called hole. And so one is electron, other one is a hole. This is called electron hole pair. This is called as a thermal generation. So on applying the thermal energy, there is a successive breakage of covalent bonds. From each bond only, what are the covalent bond who got a required energy that can able to break up? On breaking a covalent bond, one electron come to be free, and removal of electron inside the bond represent a hole. So electron hole pair. Sir, the bond is maintained, still one electron is there. So this is called the thermal generation of electron hole pair. Sir, how many bonds are broken? 1. How many electrons are free? 1. How many holes are free? 1. So for every covalent bond breakage, the electron hole pair generated such that one electron is free and one hole is free. Suppose 100 covalent bonds are broken, 100 electrons are free, 100 holes are free. So in intrinsic semiconductor, at any instant of applied energy, what are the number of covalent bonds are broken? That number of electrons are free, and as well as that number of holes are free. Such that in a pure semiconductor, number of electrons is equal to number of holes. Such that the total conductivity becomes 0. So you may get the conductivity by electrons, sir, no problem. You may get the conductivity by holes, sir, no problem. But in any semiconductor, you may always say that total conductivity is considered by the sum of the conductivity by electrons and holes. So number of electrons same, number of holes is same. So that automatically the conductivity also same, because electron and holes have the same charge, 1.6 into 10 power minus 19 coulombs. So what is the instant at which the electron come out as a free? The same instant the hole to be generated as a free. So at what time they generated, that is the same. Charge is same. Right, number is same, so current is same. Only the thing is opposite is what? Polarity. Electron negative, hole positive. So in any semiconductor, total current is considered by the sum of currents by electrons and holes. Total conductivity of a pure semiconductor is 0. That's a problem. So even you can consider the free carriers of electrons and holes, individual conductivity is there, but in a semiconductor, individual conductivity not considered. Overall conductivity can considered by electrons and holes, that should be 0. So a pure semiconductor have a 0 conductivity. So how to improve the conductivity, sir? The conductivity of a pure semiconductor can be improved by adding some impurity. Adding some impurity to a pure semiconductor. The process of adding impurity is called doping. The process of adding impurity is called what, sir? Doping. So, right, the process of adding impurity called doping. The resultant is a doped or extrinsic semiconductor. That's the case. Understand, students? So, covalent bond is obtained by, so adding a covalent bond is obtained by sharing of one electron from each neighbor atom, students. Covalent bond is a crystalline structure and a cumulative I can call. Okay. Every covalent bond containing electron pair. What is that condition you say? With applied energy, right? Energy to covalent bonds increases, right? Energy to the covalent bonds, what, sir? Increases, I told. What is the minimum energy required to break a covalent bond, students? The minimum energy required to break a covalent bond is equal to energy gap, students. Is equal to energy gap, that is around 1.12 electron volt for silicon. I can call at room temperature, right? So understood now. When a covalent bond broken, how many electrons are come out? When covalent bond is broken, right, one of electron pair come out as a free, students. Come out as what? Free, right? And removal of electron generate a hole. That is breakage of covalent bonds. Breakage of covalent bond causes electron hole pair called thermal generation, students. Thermal generation, you say. Confirm? So in this pure semiconductor, you say number of electrons equal to number of holes. So that total conductivity, what, students, is 0. Total conductivity is 0 in a pure semiconductor. Even you can generate the carriers, right? So the conductivity is increased by making what, students? Making this to be different, one to be more than other, right? Making either electron or hole to be excess, and is done by adding impurity called doping. Students, and the result is a doped or extrinsic semiconductor. What is that? Doped or extrinsic semiconductor you discuss, students, and depending on the type of doping, you may find out two type of extrinsic semiconductors. One is N type, other one is P type. Understand now, students? Up to this, I think that it is clear to you. So in the next session, you can discuss what is that doped or extrinsic semiconductor, then current mechanism. After that, you discuss that generation recombination condition. Then I can start that diode concepts. Okay, understand all these things, students? Thank you. All the best.